Since ancient Greece, the subject of light has been a subject of interest and investigation for philosophers and scientists alike. Light has always been of interest to philosophers because of its direct relationship to vision. We can see things better in the light. So it's kind of always been assumed that there is some sort of relationship between light, vision, and color. Nevertheless, some deceptively simple questions have existed since the beginning of philosophy concerning the nature of light. What exactly is light? That is to say, what sort of thing is light? Is light the same sort of thing as, let's say, a tree? In other words, is light composed of some sort of stuff, to use technical language, as a tree? It is apparent from the night-day cycle that there is some sort of motion related to light, at least to the source of light, such as the sun. This is related to the first question because if light is a thing, and it's a thing that moves, then how exactly does light move? When we look at nature, all forms of motion take place in some sort of a medium, or a thing through which something moves. The medium of a fish, for example, is water. A fish moves through water. With respect to light, what sort of thing does light move through? The 16th and 17th century saw the rise of mechanistic philosophy and science, and with it came a new explanations concerning light and its motion. A popular explanation that emerged was the lumiferous ether. Lumiferous here meaning light-bearing, or the medium that light is moving through. Sorry if I butchered that pronunciation. Ether was a hypothetical medium that was thought to permeate all of space and allow for the transmission of light. By space here, of course, I mean outer space, as well as the space on Earth, but substances like air and earth were composed of a different material than ether was. Ether was proposed to be a substance through which electromagnetic waves, including light, could travel or traverse through. One of the main problems that was trying to be addressed here was how exactly light moved from the sun, an obvious source of light, to the earth. Consequently, the ether was proposed as the medium through which the light moved. Robert Boyle was one of the first modern proponents of the ether hypothesis. According to Boyle, the ether is composed of subtle particles and that there were different types of these particles. One of these particles clarifies the absence of a vacuum, the vacuum in space, and the mechanical interactions amongst bodies. So, for example, explaining the motion of the planets. The other type of substance or particle that Boyle mentioned related to properties such as magnetism that were observed in nature and potentially gravity, although gravity wouldn't be fully developed, of course, until Newton. After Boyle came Christian Huygens in his treatise on light in 1690 proposed the idea that light functions as a wave, moving through the medium known as ether in a wave-like pattern. Huygens argued for an atomic theory of matter in which the material world is composed of particles which, quote, touch each other without composing a continuous whole. Light in this view is the disturbance which moves in a material medium, that is the medium composed of particles. This ethereal matter is composed of elastic particles of matter which transmit the light. According to Huygens, this wave theory of light provided a framework for understanding various optical phenomena, emphasizing the role of ether as the medium through which light travels. After Huygens came Newton, who presented his particle theory of light as opposed to the wave theory in his Optics, which was published in 1704. Newton proposed the particle theory of light, suggesting that light is composed of tiny particles, which were referred to as corpuscles. Corpuscular theory, I think I pronounced that right. Corpuscular theory was kind of a deviation of atomist theory, but corpuscular theory was used to explain all sorts of different things from the senses, such as smell, to the senses such as sight, that these corpuscles are what was transmitting the sensation itself, or rather the experience of the sensation, I should say. According to Newton, these corpuscles traveled in straight lines and exhibited different colors based on their size. He argued that the phenomenon of refraction could be explained by differences in the speeds of these particles in different mediums. Newton, writing to Henry Oldenburg about his recent experiments with colors, states that for assuming the rays of light to be small bodies emitted every way from shining substances, those when they impinge upon any refracting or reflecting surfaces must as necessitate excite vibrations in the ether, as stones do in water when thrown into it. Newton's corpuscular theory of light postulated that light consisted of these tiny particles which were emitted from objects, such as the sun, and traveled from one point to another via the medium of ether. Newton's theory, because of his status as a physicist, became more popular at a time, and as a result, the theory of light as a particle would dominate physics until the 18th and 19th centuries. The medium through which light traveled, consequently, would theoretically impact its speed. The operative analogy here is that light moved or vibrated through the ether in the same way that sound moves through the air. Newton's understanding of light as a particle was not seriously challenged until experiments of the English physicist Thomas Young, who demonstrated that light moves in wave-like patterns, most notably from his famous double-slit experiment. Nevertheless, Young still had to posit the existence of the ether in order to account for the problem of what exactly light was a wave of. If ether was the medium through which light traveled from objects like the sun to the earth, then it ought to be possible to measure or detect the effects of ether on solid bodies like the earth, which moves through it. Towards the end of the 19th century, especially with the rise of the new field of electromagnetism, the concept of the ether was growing increasingly problematic. James Clerk Maxwell would write in the Encyclopedia Britannica in 1878, ethers were invented for the planets to swim in, to constitute electric atmospheres and magnetic effluvia to convey sensations from one part of our bodies to another, and so on, until all space has been filled 3 or 4 times over with ethers. The only ether which has survived is that which was invented by Huygens to explain the propagation of light. The Michelson-Morley experiment was conducted in 1887 by Albert Michelson, I keep calling him Michelson, and Edward W. Morley. In the experiment, they used an interferometer to measure any differences in the speed of light in different directions, anticipating that the Earth's motion would cause a detectable variance. Michelson-Morley devised an experiment that would be able to demonstrate the relative motion which occurred between the ether and the Earth by simultaneously measuring the time that it takes light to travel a fixed distance. Performing such an experiment theoretically would provide a quantitative measurement of what was known as ether drag. Ether drag being a force which would impede upon the speed of light. Remember, according to earlier wave theory of light, it was believed that light waves required a medium to travel through, similar to how sound waves travel through the air. Ether drag was a hypothesis within this framework that suggested that the Earth, as it moves through space, would drag or carry the ether along with it. This dragging effect would potentially influence the speed of light in different directions in the same way that an object's traveling through the air would be impacted and influenced by the speed of the air through which it was moving. Okay, so I'll do my best to explain how the experiment was set up here, but I have a nifty illustration that I ripped from the pages of Wikipedia. So in the blue box here, you have the light source, that which is emitting the light. The light is emitted. It's going to hit these mirrors. So this is a semi-silvered mirror, and what that means is that this mirror is going to block some of the light that's going through. Now, the light that goes through is going to be reflected to 2 other mirrors, one mirror up here, another mirror up here. It's going to bounce off of both of those mirrors, come back through the silver mirror, and hit the detector. Now, my explanation of that probably sounds pretty convoluted because it is, but the idea behind this is that you're getting light coming from 2 different sources and from 2 different directions. And the idea is that if there was an ether and if there was an ether wind kind of moving through this space, then you ought to see at least a variable degree from the light coming from one mirror being different from the light coming from another mirror, that there just should be some sort of impact of the ether wind on the speed of the light. The results of the finished experiment were underwhelming, and Michelson was unable to observe any effects of ether drag. The results of the experiment were, to quote Michelson and Morley, quote, that if there be any relative motion between the Earth and luminiferous ether, it must be small, quite small. The Michelson-Morley experiment demonstrated that the intensity or speed of light was not impacted in any observable way by the existence of an ether. As a result, Michelson was forced to conclude that the results of the stationary ether must thus be shown to be incorrect, and the necessary conclusion that follows is that the hypothesis is erroneous. Michelson wrote about the decisively negative results in a letter to Lord Rayleigh in August 1887. This is what he said: "The experiments on the relative motion of the Earth in the ether have been completed, and the result is decidedly negative. The expected deviation of the interference fringes from above zero should have been 0.40 of a fringe. The maximum displacement was 0.02, and the average much less than 0.01, and then not in the right place. As displacement is proportional to the squares of the relative velocities, it follows that if the ether does slip past the relative velocities, it is less than 1/6 of the Earth's velocity." The Michelson-Morley experiment aimed to detect the motion of the Earth through the ether. However, the experiment yielded a surprising result. The impact of the ether on the Earth's motion was negligible. This unexpected outcome posed a challenge to the prevailing understanding of the nature of light and led to a reevaluation of classical physics. Albert Einstein's theory of special relativity, developed in 1905, provided a revolutionary explanation for the Michelson-Morley experiment's results. Instead of relying on the existence of ether, Einstein proposed that the laws of physics are the same for all observers in uniform motion, and that the speed of light is a constant for all observers, regardless of their motion relative to the source of light. Einstein's theory of relativity not only explained the Michelson-Morley experiment's findings, but also transformed our understanding of space, time, and motion. It marked a departure from classical mechanics and laid the foundation for modern physics. In essence, the Michelson-Morley experiment played a crucial role in inspiring and validating Einstein's groundbreaking theories. In addition to Einstein, the Michelson-Morley experiment also deeply impacted philosophy. In the writing of the French historian of science Alexandre Corre, as well as the American Thomas Kuhn, and the perception of how science progresses through its history. I hope that you enjoyed this video, and I will see you all next time.